Hello, calculus fans. I am going to go through a particular exam 2 from winter 2023, as I've been trying lately to see if a video would help. Do remember you can find my old exams on my exam archive. If you do a Google search for Andy Lovelace, UW exam 2 consists of mostly integration plus a few other topics. I have a review here, and it's always going to depend on the quarter, but we do the full breadth of integration, and then possibly something about volumes or work or average value, approximating interval. There's this section 7a. This is an old review sheet that's about improper integrals. So I have reviews on all those things here. There's an integration table. There's lots of particular practice. If you've completely forgotten a topic, you can look back at old notes for that topic. So that's all stuff that's there. So assuming we have a general idea, I'm going to try to be as efficient as I can and work through most of this exam in 15-20 minutes. But let's see. So for the sixth exam, I like to give this table because this is the table we provide on the final, which is kind of a minimalist table of the integrals. In my class, I give a few more in class, and you can quote those as well, but you'd need to put those on your own sheet. Okay, so let's think through the process. So as I talked about in class, when you are given an integral, there's a certain thought process. You're always looking to simplify or do substitution. But there's a few things that jump out to you, right? So if it's a product, log, or inverse trig, you're thinking by parts. And so that's what jumps out at me here. And so I would immediately write down by parts. I think this is one of those things, if we prepare, this is definitely something I've talked a lot about in my classes, but products, logs, inverse trig. So what told me that? The fact that there was a log there. There's really not much else I can do. And the whole reason we do this is because I know the derivative of a log. If I don't know the antiderivative, well, I might know a version of it. Now, there is maybe one question of what's the rest. I sort of remember some students saying x cubed. But it's as if you just took the log of x out. What remains? What remains is this, which is the same as x to the negative 3. So I think that was the most common error. But that's mostly just care. I mean, if you put those two things together, it should look exactly the same as this. Okay, now we're integrating, so the power should go up. So this is going to be a negative 2. This is going to be a negative half. And then you just go. Smush these together. That's UV. So it's going to be negative. If I was going to write this, I probably would simplify it. So I'm going to put these together in the way that looks most pleasing to me. 2. And these little maneuvers are helpful. Writing things in an ugly way is hard for you. It's hard for the grader, but it's hard for you. Minus the integral, and then I put these together. And if I was going to put those together, I'd like to write things in a nicer way. This is negative 1/2, 1 over x squared. So when I put those together, I should see that it's negative 1/2, 1 over x cubed. And this is negative log of x, 2x squared, and then plus 1/2, whatever this integral is. So now I'll be a calculus student again. I talk a lot in class about how when you're doing algebra, negative exponents are weird. But if you're doing calculus, they're helpful for our rules. And this is pretty common where you do integration by parts and you happen to get a very similar integral to part of what you did on the second go round. This is going to be power goes up, so it's negative 2. We're going to divide by negative half, so it's going to become negative 1/4 plus c. Then it just depends on how we want to write it. Again, in my class, we would accept that as an answer if it's correct. But if we're going for the pretty prize, we might write this. Ooh, can I do better? If I wanted to write it prettier, I might multiply top and bottom by 2 and factor out the negative. So I feel like I'd like to say, anyway, what I'm saying is this: put a 2 here, put a 4 here, and the denominator's the same. And so I would say negative 2 log of x. So this would be my vote for prettiest answer. Okay, as I like to do, I found when I make these videos and I have a typo, people go nuts. So let's pull up my solutions just to make sure I didn't do something silly. But that definitely should be products, logs, inverse, trig. We should immediately know by parts. And I get a deduction there because I didn't put my plus C. Okay, on to the next one. Trig integral. So we have a set of strategies. The way we think on a trig integral, this was section 7.2 if we need to review, is you're either trying to set up a substitution, or if there's one special case that involves half-angle identities. But that's only when you have even powers of sine and cosine. So most of the time you're setting a substitution, which means you're trying to pull something out so you can use one of your substitutions. Now in this case, we have a mixture, so I would want to rewrite it. So there's a little challenge here, which is there an obvious way to rewrite this? And it might help you to think about it this way. And when I look at it that way, I realize, oh, it kind of would be nice to turn this into a secant squared. And so really this was the same as this. That was a lesser issue. Secant to the fourth. So now I know I'm going to do a substitution. It's just a question of which one am I going to do. Am I going to do secant? Or am I going to do tangent? If I do secant, I need to pull out a secant tangent and change everything else to a secant. The way we do that is we say tangent squared of theta is secant squared of theta minus 1. So that's one option. But that's not going to work very well here. That works better when the powers are odd. And the reason is when you pull one out of an odd, you get an even. You can use this identity. So the other option is this one. And this one works better when the power on secant is even. And then we're going to use the same identity, just written a different way. With me, I definitely have these identities on my note sheet. So anyways, I'm going to pull out a secant squared. Factor it out. And then I'm going to ask myself what's left standing. And what's left standing is a tangent squared and a secant squared. So I'm not doing this. So I'm going to replace every tangent with a u. So this is going to be u squared. I'm going to replace this with a du. And then, so even if you forgot the method, you'd get to this point where you're stuck and you'd say, I wish that was a tangent. And that's when you use this. This is tangent squared of x plus 1. So this is going to be u squared plus 1. And now we're almost done. So now you expand. And you write 1/5 u to the 5th plus 1/3 u to the 3rd plus c. And then we're done. 1/5 tangent to the 5th of x plus 1/3 tangent to the 3rd of x plus c. Success. So fairly standardized. You do need to know the plan. I mean, I wouldn't want to, if I hadn't thought about these, this would be tough, but we've done quite a few of them. All right, let's take a look. Make sure I didn't do anything silly. That looks the same to me. On we go. So there you go. I always have this in my mind. You would then step back and say, on my own, could I do that page in 10 minutes? I think that's doable. How much time have I spent? 9 minutes with the intro and the explanation. Okay. Let's keep going. So then I see this, and this immediately should make us think partial fractions. It's reduced because the power on top is smaller than the power on bottom. And so this is just step 1 is to factor. It looks like I can factor an x squared out. Well, I feel like I've done this one already in another video because I think this was in a test prep. Plus b. And if you've forgotten how to decompose, that's what that whole section was about. We say this is a repeated linear term. We say this is a distinct linear term. There's these three terms. We cleared the denominator. And then we have two things we can do. We can plug in special values that make one side 0. 0 is a good choice here because it makes this 0 and that 0. So you get b times 2. You get b is 8. Negative 2 is a good choice because you get 20 on the left equals c times 4. I know I did this in a different video. And then lastly, I'd compare coefficients. I'd compare the coefficient of x squared would be the fastest in my opinion. Because on this side it's a plus c and on the other side it's 1. And so that tells me that a is 1 minus c, which is negative 4. And then we're ready to be done. So yes, I know some people are slower than others, but if you know the ideas, I mean, that if you can integrate but it takes you all day, that doesn't really make it that helpful. We want to be able to do this quickly here. Okay, so we're going to have negative 4 log of the absolute value of x plus 5. Both of those are linear, so they fit our log rule. This one is not linear, so we're going to think of it as this. And when we integrate, it's going to become negative 1. So I'd probably write it this way. Done. So that was a somewhat straightforward partial fractions problem. Let's double check and see if anything went wrong there. Success. On we go. Okay, this jumps out at me as something that has a square root and has a quadratic. That's a very particular method we learned called trig substitution. But in order to use it, you can't have this middle term. So we talked about how you do half the middle, squared, so it's just 1 squared, so it's just 1. And that should be a perfect square. And you can double check and make sure it is. But you can't just do that. You have to account for the 5 that was already there and the fact that you just threw in a 1. So let's subtract the 1 we added. Let's put a 5, and you say, oh, that's positive 4. It's very important you get that all right. It's worth your while to stop for a moment and re-expand, because you don't want to move on unless you are 100% certain that's the same as what you started with. Okay, so then you kind of take a breath and you rewrite the problem. And I've been encouraging my students just this quarter, based off of some of the issues I've been seeing, to rewrite it as a square root cubed in this case. The other thing, and this is kind of new this year for me, because I usually just do it directly, but some of the mistakes I've been seeing are based off of the fact of simplification error here, which makes me think maybe I should recommend doing this substitution. Now, this is not necessary, but I've encountered probably a dozen students in office hours who made an error that probably would have been prevented by taking a moment to do that. It just makes it so some of the simplification can be done before it gets more complicated. You do have this issue of what to do with this x, but x is t minus 1. We've played that game before. And we're going to multiply that times 4. So I would completely simplify it like this, or take the 4 out. I'm good either way. Okay. That's kind of step 0. We haven't done anything yet. We just rewrote it so that we can use trig substitution. And now we should know, because there's a plus, that we would like to use 2 tangent. And the entire reason of this method is what happens when you place this in here. This is the whole reason the entire method is about getting rid of that square root and the fact that it simplifies. So then you can factor this 4 out. You get 1 plus tangent squared. This is why we use a tangent when it's a plus, because we can use this identity. And so that's 2 secant of theta. And now we're ready to go. So it's going to be 2 secant of theta, and that's going to be cubed. And I've seen people mess up the algebra here, so that's why I'm suggesting separating the square root and the cubing. Trying to help build good routines. And ultimately, we would like our algebra to be good enough that we don't make mistakes like that. And calculus is where you learn your algebra, because it's there's huge penalties for getting it wrong. Okay, but don't forget dt. Very common that people forget that in the midst of doing everything else. And then let's clean it up. Now I think I do want to factor out that 4, just bugging me a little bit. 2 tangent of theta minus 1. So now I wish I would have taken the 4 out back there, but this is going to be 8. And you should take your time here. Really, the problem itself isn't that bad, as long as you get the beginning right. And that should clean up dramatically, and it does. You can cancel this and make a 4, and then you can cancel that and make a 1. Ooh, that's nice. And so you're just left with 2 tangent of theta minus 1 over secant, because the square and the cube. Now what? Well, we're done with that piece. Now we have a trig integral. We're going to need to recognize it, and I don't recognize it. So I probably am going to have to rewrite it. But that doesn't scare me. So I'm going to split it into 2. Tangent of theta over secant of theta minus 1 over secant of theta. I still don't recognize those. But 1 over secant of theta really makes me start to think, oh, that's cosine. And that then gives a hint kind of out the previous one, because this is going to be sine of theta over cosine of theta all over 1 over cosine of theta. That's just sine. Multiply top and bottom by cosine, you get sine. So this is one of these where it might look bad, but if you just take a moment to simplify, you got it. And so the trig integral is actually very fast. Negative 2 cosine of theta minus sine of theta plus c. That step's done. And trig substitution has these 3 very clear steps. We just happen to have a step 0, which we had to do before we could get started. And the very last of the steps is, how do we return to x? And that's where we go back and we say, hold on, I know that tangent of theta is t over 2. And the reason we write it as a fraction, not using good use of my space, is so that we can label the ratio that this represents. And then we can solve for the other side. This squared plus this squared equals that squared. So this is the square root of t squared plus 4. And then we're ready to go. Cosine is adjacent over hypotenuse, so it's going to be 2 over square root of t squared plus 4. And sine is t over 2. And then finally t was x plus 1. So negative 4. You know, incidentally, if you really wanted to make it look nice, you already know that when you put in an x plus 1 there, it's going to come out to be that same expanded version. So I think I'm going to write it in the nice form we started with. Minus, and we said t was x plus 1. And that's great. Small comment, just because I see it, is if you distributed, this term would be negative x over 2 minus a half plus c. And an online calculator would never do that. It would just call this d or some other constant. And they would write their answer as -4 square root of x squared plus 2x plus 5 minus a half x plus c. Sometimes that really confuses people, but it's if the only difference between your answer and someone else's answer is a constant, it means that your c and their c are different, but you're both right or both wrong. Okay, let's see how we did. See if I did a sign error or anything. Okay, we saw that one. Here we did the trig sub. I did make a mistake. See, this is an example of me not being very careful. Does anyone spot the mistake? I can't add. That's what I would say in class, and I'd have you point it out. Oh, things were going swimmingly until that moment. The mistake's right here. That is not the hypotenuse. Sine is the hypotenuse. So there we go. Again, that's why I check the solutions, because I'm prone to mistakes. I'm a human being. My mistakes tend to be miscopy mistakes. So you got that little bonus chat for free. My apologies. I'm still going to get an email about it, I'm sure. Because people are like, I spotted this error. But just because they stop the video before they see me check it. Oh well. I could edit it out, but I'd rather you get the true feeling of what we're doing. And understand that I make some mistakes too. Again, a student that made that mistake might just lose 1 point, but I would have gone back and checked my work. I might have found it, but I don't want to give myself too much credit. Okay, on to question 3. This one probably is the hardest one on the test because it doesn't nicely fit. All the rest we've done so far directly fit into one of our methods. So this one's trouble. Now this one's also almost directly from the homework, so my students hopefully would have an idea because they just did a problem like this. But the answer, when it doesn't perfectly fit our methods, is to try a substitution. And we've talked in class how probably this substitution is going to work. It's called a rationalizing substitution, and the square root goes away. But honestly, if you chose this, that's probably going to also get progress. If you choose the denominator, it's probably not going to work very well, but you could try. But this is the way to go. So through practice and through doing homework, you'd have an idea. Now, the one thing that makes your life easier here is squaring both sides, simply because the derivative is easier to take. It's easier to plug in. So I'm going to do this substitution. Okay, the bounds then become, and it's worthwhile to change the bounds because it just makes things easier from here on out. You plug in a 5, it's going to be the square root of 4, so it's going to be 2. So if you plug in a 5 there. Okay, so those numbers are already nicer. The numerator becomes t. That was the thing we were trying to get rid of, and we did it. The denominator, unfortunately, gets a little worse. This is going to be t squared plus 1 plus 3, and dx is this. And I think I've done this one already in one of the videos, so it's going to go from 0 to 2t squared. Ah, yes. Now it's a rational function, but it's an irreducible quadratic, so it's broken down as far as it can be, except it's not reduced. This is a long division problem. This goes in there twice. This would be 8. Subtract -8, and we're done. There are a lot of little skills. Worst case, you miss one along the way. You could do that problem with trig substitution. It would solve it. So even if you didn't see the division, it just would be a little longer to do it that way. Because at this point, we're done. This is 2t. This is minus 8 times 1/2 log. Oh, that's not funny, but I made the mistake the students always make. My brain was thinking of something else for a moment, and I lost my focus. This is t over 2 plus c. And so this is 2. These are long videos to make, but I hope they're helping you. Arctangent, not plus c, we're evaluating. So actually I just wasted time there. I do not need to return to x because I changed my bounds. I made it so I didn't have to do that. I think if you plug in a 0 everywhere, you get 0, because arctangent of 0 is 0. So what you're left with is 4 minus 4 arctangent of 1. And arctangent of 1 is one of our nice, well-known values. I did do that in another video. Well, shoot. It could have been from a different exam. Sometimes, I reuse a question many years later. That might be what happened here. Okay, so then we have yet another trig sub. This one doesn't have completing the square, but it has some different challenges. This one is a very important classical example that I spent quite a bit of time on. It's one where you get sine, and when you substitute in, you get this. Sine, sorry. So it's 9 square root 1 minus sine squared. And so it's the square root of 9 cosine squared. If you can do that in fewer steps, that's fine, but I'm just doing this to re-explain. So this becomes 3 cosine of theta, but what did we forget? We forgot dx. Dx is 3 cosine of theta d theta. Okay, step 1 is done. This then gives me 9 cosine squared of theta. Didn't have to complete the square that time, so there was no step 0. Now we've landed, earlier in this test, we've done a few trig integrals already. We did this one we did substitution, and I reminded you about the technique. This one we had to do a trig integral, but it's simplified. And this one has an even power of cosine. That means we're doing half angle. So 9 halves, 1 plus. So you need a couple of these plans. I don't know what you're going to do. So it's going to be 9 halves, and that's going to be theta plus 1 half sine of 2 theta plus c. And there's another piece to this. And the piece here that we talked about this because this was such an important special case. So it's one that I even gave an entire identity to help you with. So when we try to return, and we solve for sine, and we say it's x over 3, that means opposite over hypotenuse, and that means this is 9 minus x squared. The issue is this is 2 theta, which has nothing to do with that triangle. But there is this identity. That's where we use that other half angle identity I mentioned, which that this is cosine of theta, sine of theta. But definitely if you did the homework, you encountered that a few times, and we did that in class. So wrapping things up, we can then say this is inverse sine of x over 3. Cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. Plus c. I can see that the 9's cancel, so I'm going to simplify a little bit. Arc sine of x over 3 plus, I think 1 half is all you're left with. There we go. Very classic example. Let's go through. I didn't check this other one. Yep, pi at 4 minus pi. Yep, there's our example. So that's a collection of common integrals of each type. The challenges are when you have to do some substitution along the way. But hopefully that's of interest to you. Okay, so now the last couple of pages of the exam I typically devote to the other things we've done. Now this one is an improper integral, and we will talk about this if we haven't yet in section 7-8. Often this is the last thing we do before the test. The most important thing is realizing it's a two-step process. So anytime there's some sort of asymptote, I'll usually use the t. It's asking, does the area approach something? And so your job is to find the pattern for the area and then ask what happens. So it's an important ordering. We don't actually plug in infinity. That doesn't make sense. So you have an integral to do. Now this integral is just straight simplification. You don't need any special tools here. This is x to the negative 2. This is x to the negative 3/2, because this is x to the 1/2. So actually we're ready to go. This is the limit as t goes to infinity. It's the integral from 1 to t to the negative 2 plus x to the negative 3/2. So you don't need to substitute. I mean, you might have been tempted to do that, but you should always look to simplify if you can do it. Okay, now we are going to keep integrating. This is going to become negative 1 with a negative. This is going to become negative 1/2 with a negative 2. Evaluate it from 1. And you don't worry about the limit until you're completely done simplifying. This is going to be negative 1 over t. And this is a comment of, since I know I'm going to be thinking about what happens as t goes to infinity, I really would like to simplify. Okay, and then we're going to say minus, and we plug in a 1, negative 1 over 1, negative 2 over the square root of 1. And when all is said and done, I'm trying to take the limit as t goes to infinity of negative 1 over t minus 2 over the square root of t. And this other thing is plus 3, I think. So it's 1 and 2. So the actual taking of limits sometimes scares students. We'll review this in section 7-8. The vast majority of the limits in that section are really, really fast. And this is one of them. This just goes to 0. This just goes to 0. The answer is 3, and it converges. That's it. So it's not a huge topic. There are some important applications in future courses, so we talk about it a little bit. But there you go. Okay, what in the world is this one? We're given this table. It's a not table. We're given this graph with a bunch of data points, and it says, using the values, so it's a Simpson's rule question, with 4 division, we would like to know what this is. And what they're asking is, this looks like a volume. You don't have to know that it's a volume, it's just telling you to compute. But, sorry, I mislabeled. It's a volume in terms of x, so they're talking about washers. But you don't even have to think about that, you just have to compute. Sometimes you'll just don't remember how to read graphs, but this is saying that f of 5 equals 4. But even if you're confused on that, there is a systematic way to do this. You do the delta x is 8 minus 0 over 4, which is 2. You label your tick marks. Your first tick mark is the leftmost point, and then you just keep adding the width, which is 2. This is 2. So you can do this without really thinking. This is 4. This is 6. This is 8. And so I'm going to have tick marks here, 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 here. Okay, now we're trying to approximate. Use the integral as your guide. So let's do a few things. The delta, we know this is going to be 2 for our approximation. Let's factor that out. We also know we can factor out a pi. So I would factor out a 2 pi. And then I'm going to have, what else? Simpson's rule says that you do 1/3, so 1/3, and then you do f, not f. You do your integrand, which is this. And then you do it with a 4. Then you do it with the 2. Then you do it with the 4. Squared, sorry, I miscopied. And you wouldn't even need to write this. I'm just explaining. But notice how you should have your entire integral here. So let's just circle the things. That is there. I just chose to factor it out. The width is here. I just chose to factor it out. The rest of this, I'm just kind of commenting because I've seen sometimes people just blindly use f of x, but by f of x we mean whatever the integrand is. And the last step is just plugging in. So the bounds are 0, 2, 4, 6. The tick marks I should have said. And the table actually makes our job easier. I mean, what I mean by the table is the picture, because you can read these off. F of 0 is 1, so this is 1 squared. I just saw that right there. F of 2 is a half, so this is plus 4 times a half squared. F of 4 is 2, so this is 2 times 2 squared. F of 6 is 1, so this is 4 times 1 squared. F of 8. So I think students that struggle in this just sort of panicked because they're like, oh, there's a table, I don't know what to do. But when I wrote this question, part of the complaint about questions that involve Simpson's rule is the tediousness of them. So I was trying to make something that was shorter. I think in doing so, I confused people more. What do they say? Good intentions never go unpunished. 20 pi over 3. Let's see how we did. 28 pi over 3. Did I add something incorrectly? Possibly. Did I miscopy a number? That is 10. I don't see a mistake, so let's go look. 1, a half, 2. Oh, when you plug in a 2, it's 2 squared. So that's not going to be 4, it's going to be 8. I did have a mistake, darn it. It's because I was telling some dumb joke. So this is 14. This is 28. Oh, you hardly even know what happened. All right. Finally, we have some work questions. That's a topic unto itself. A leaky tube on a bucket is lifted from the ground to a height of 10 feet at a constant speed with a rope that weighs this. How much work is done in lifting the leaky bucket alone? So here's the start. It's leaking. You can set this up however you want. If you decide you want to call the ground 0, maybe I'll use, just to emphasize, you can do whatever you want. Maybe I'll label the ground y equals 0. And I'll label the top y equals 10. And this is one object that's getting lighter as it goes. And what we're going to do is sort of picture how much work is done in each of these segments. Meaning from here to here, how much work is done. We're going to call that delta y. So in this setup, we're thinking of that as the distance. And the question we're going to ask is, when it gets there, how much does it weigh? So here's what we're saying. For a given y, meaning if you've lifted it already to y, we will estimate the work to lift up to y plus delta y. to lift a little more. And then we'll add those up. So in other words, the distance lifted, this is how we thought of all leaky bucket problems, is delta y. In this case, that's feet. Now we need to know how much it weighs. And what did they tell me? So the force, they said it's changing at a constant rate. It's linear. So what do we know? We know that it's 2 pounds. It contains 20 pounds of water, but the water leaks and finishes draining at the top. So when it's at the bottom, the force is 22 pounds. And when it's at the top, the force is 2 pounds. And because they said it was linear, I have this function. So some people are confused when you're given a y. But this is it. So my plus b. I chose to label it y, so that's why it looks confusing. But so I have 22 minus 2 over 0 minus 10. And these numbers would be different if you chose a different labeling. But I'm getting negative 2. The y-intercept is 22. That's the value when it's 0. So I'm getting the force is negative 2y plus 22. The good news is you can check all of that by just plugging in some numbers. When you plug in 0, it's 22. When you plug in 10, it's 2. Great. Now I'd like to add those up. So officially what's happening, you don't have to show this, is we're adding for each y, if you broke it up into subdivisions, we're doing the force times the distance. And then we would like to figure out what happens if you did that with more and more subdivisions, and that just becomes the integral from 0 to 10 of negative 2y plus 22 dy. And honestly, you could do all of that without saying all those words. It would be much shorter. I was just explaining. So this becomes y squared plus 22y from 0 to 10. When I plug in 10, I get negative 100 plus 220. So I think that's just 120 foot-pounds. Oh, I bumped something. Just a moment as I try to recover. Okay. Then it says how much work was there to lift the rope. This is just one approach to the problem. This quarter I broke it up for people completely. I have a certain way I like to do rope problems, as I've talked about. So for this one, I'm just going to label it differently just to illustrate some different labelings. But I'm going to label this time the top x equals 0 and the bottom x equals 10. For rope problems, this is often a good way to go. And I'm going to start the same way. I'm going to break it up into a bunch of subdivisions. But now there's a different story. If you compare these two things, each subdivision was like a distance you lifted. In this case, every subdivision already contains some rope. And so we're going to say if you give me a particular x, and you give me a segment of the rope that has thickness delta x, so given a segment of rope of length delta x feet, that is x units from the top. We will find the pattern for the distance lifted and how much it weighs. In this case, the distance lifted is going to go from there to the top, so the distance lifted is x. And that's the fundamental difference between leaky bucket problems and what I like to call stack of book problems, because it's like we're treating each one of these as a different job, and then we're going to add them up. The force is going to be how much that segment of rope, which is this long, weighs. And that's what the 0.3 is about. And so what we really would like to do is add all those up. So for any given x, we would like to do xi times 0.3 delta x. But then we'd like to do more and more subdivisions. And that's where this integral from 0 to 10 of x times 0.3 dx comes from. So there you go. There is a way to sort of do those together, but if you're doing a pumping problem, you have to think of it as a stack of books, so I like to use this. Could you label the top 0? Yes. Here. Could you label the top 0 on the first one? Yes. You can get the same answers. Okay, so what's going to happen here? This is going to be 0.3 over 2 times 100. So it's going to be 50 times 0.3. Okay, 0.1 would be 5, so 0.3 must be 15. 15 foot-pounds. It's a lot less than the bucket, but the rope, hopefully was fairly light. So our final answer, the total work is 120 plus 15, 135 foot-pounds. Let's see how we did there. $120 foot-pounds. Here you can see I labeled the bottom with an X and the top with a 10. I also gave one where I labeled the top 0 and the bottom 10. They look a little different. One has a formula negative 2x plus 22. The other one has a formula of 2y plus 2. It just depends on how we're counting, but they both give 120. Here I labeled the bottom 0, and you can see how that changed this piece, but the answer came out the same. Here I labeled the top 0. There you go. All right, I hope that's helpful to you. If it is helpful, let me know in the comments. I'm wondering if this is something I should keep doing. All right, thanks.